Maximum power of the synchronous generator, usually called the static stability limit of the generator, and actually the in practical the generator cannot achieve to this limit. This because the value of the torque angle delta cannot be 90 degree, and usually is between 15 and 20 degree. So the produced torque or the induced torque here in the synchronous generator is generated due to the two magnetic flux, the rotor magnetic flux and the stator magnetic flux. And usually the stator magnetic flux try to destroy the rotor magnetic flux. So we have something we call it the net magnetic flux. So the net magnetic flux here, which come out or which is responsible to generate the phase voltage of the synchronous generator, and the rotor magnetic flux is responsible to generate the internal voltage or the armature voltage of the synchronous generator. So the value of the induced torque will be kpr times p net or kpr times p net sine delta. This represents the value of or the magnitude of the induced torque. Okay. Uh, this will be the form of the calculating the induced torque. Actually, when we substitute for the value of the power, previously we said T or tau induced equal to B out or B converted over omega m. So when we represent the value of the P out, which is the power or the real power, equal to 3 V phase EA sine delta over XS from the previous slide. So this will give us the value of the induced torque. So the induced torque equal to P out over omega m. The value of P out equal to 3 V phase EA sine delta over XS. When we study the previous machines like the induction machine, transformer, or DC machines, always we talk about the how we can measure the parameters or the components of the equivalent circuit of the machine. Okay, so usually we have to conduct some tests in order to find the model of the or the equivalent circuit of the machine. So for the synchronous generator, we said our machine or the synchronous generator, it has some components that need to be calculated, like the armature resistance, the reactant or synchronous reactance, and also we need to find the value of the EA or the internal voltage or induced voltage of the armature. Okay, so the quantity that we need to calculate here or the test that we need to for the induction machine, we said we have three type of tests. We have the DC or the DC test in order to calculate the value of the stator resistance. Then we conduct the or the open circuit test or the no load test. Then we conduct the blocked rotor test. Here we have to conduct two tests actually in order to find the value of the EA and the value of XS and the value of RA. So RA is the armature or armature resistance, and XS here is the synchronous reactance, and the value of EA, which is the internal generator voltage or the armature voltage induced in the synchronous generator. So the first test is the open circuit test. For the open circuit test actually of the synchronous generator, the generator same like the induction in the induction machine or in the transformer. When we said open circuit, that means we are not going to connect any load to the machine. Okay, so in the case of the synchronous generator, the load usually is the electrical load which connect to the stator winding. So in this case, the open circuit test, that means we are not going to connect any load to the stator winding of the synchronous generator. Next, actually, after we run the synchronous generator, the field current is in the beginning. The field current will be set to 0. That means no field current, and we said the field current of the synchronous generator usually is provided by using a DC source, either separated DC source or an exciter, which is actually attached to the camshaft of the synchronous generator. So in the beginning, the field current will be set to 0. So that means there is no current or no DC current will go through the field windings. After that, the field current will be increased steps, and the phase voltage will be measured, or uh, and in this case, the phase voltage is equal to the internal voltage because we do not have load, and since there is no load, the voltage that we have only the voltage that will be induced in the armature winding. Okay, so it is AA. Since the armature current in this case is zero, no armature current. Why there is no armature current? Because we do not have load connected to the armature winding or to the stator of the synchronous generator. So from this measurement, I mean, when we increase the current or the field current, we are going to measure the EA or the internal voltage. We are going to obtain the open circuit characteristic. So the open circuit characteristic curve is shown here. So it's show the relation between the V terminal. Actually, V terminal in this case is the same as EA because we do not have any load, we do not have any armature current, and the variable here is the field current winding. So as the field current is increased, the relation or the voltage or the terminal voltage will be increased linearly in the beginning, and this the linear relation in the beginning due to the low reluctance of the core of the armature. Actually, the core of the armature machine or the core of the synchronous machine will allow for the magnetic flux to transfer from the rotor to the stator. So there is no reluctance. The reluctance is very small, and the reluctance of the core is lower or much lower than the reluctance of the air gap between the stator and the rotor windings. So when the core reach to the saturation point, so then as we increase the field current, the the voltage will be increased slightly, not like in the beginning. See, in the beginning, as we increase the field current, the voltage will be increased very fast. Then, when reach to the saturation point, start to increase, but gradually or slowly, comparing with the case of the reluctance or of the magnetic flux in the air gap. Okay, so this the open circuit characteristics of our we call it the open circuit characteristic of the synchronous generator, which obtained by you conducting the open circuit test. The short circuit test actually for the synchronous generator is conducted by connecting or by short circuit the armature winding. I mean the armature winding or the field wind. I mean the terminal of the generator here. So the generator is rotated at the rated speed. All the terminal are short circuit, and when we said all terminals, since we have three phase, so since it's three phase, that means the three terminals of the generator will be short circuit. The field current is set to zero at the beginning, same like we did in the open circuit test. Then the field current will be increased in steps, and at the same time, the armature current will be measured. Why here we have armature current? Because the terminal or the terminal of the armature here will be short circuit. So since we have short circuit, that means we do have a current which flow through the short circuit of the armature terminal. Okay, so the synchronous generator terminal will be short circuited and the current will be increased. So we need to measure the current using a meter to measure the current, either the current of the field and also the current of the armature, which is represent in the normal case the current of the load. Okay, so then we plot the relation between the armature current with respect to the field current, and this we call it the short circuit characteristic. In the previous test, we draw the relation between the internal voltage or the armature voltage, which is EA, with respect to the field current, and we call it the open circuit characteristic. And in this test, we are going to draw the relation between the field current and the armature current, which we call it the short circuit characteristic. And as you can see here, this represents the relation or the characteristic short circuit characteristic of the synchronous generator. Show the relation between the field current and the armature current. As the field current increase, the armature current will be increased linearly. Okay. So the short circuit here is a straight line. A straight line since for the short circuit terminal, the magnitude of the armature current is given by this formula. So we can see here EA equal to EA over IA equal to EA over RA square plus XA square. And we said RA represent the armature resistance winding, and XS represent the synchronous reactance of the synchronous generator. As we can see here, this is the equivalent circuit that we see before for the synchronous generator here, and the equivalent circuit is consists of the internal voltage or internal or armature voltage here, and synchronous reactance in addition to the armature winding resistance or RA. RA here is responsible for the copper losses. XS here is the synchronous reactance, which we calculated when we consider the effective and when we consider also the different frequencies for the XS here represent the synchronous reactance, which come from the XA or the armature reactance, in addition to the consideration for the frequency of the rotor windings. Then we have the value of the voltage terminal here, which equal to 0. Why 0? Because when I have short circuit, the voltage will be 0. If I have open circuit, the voltage will be there, but the current will be 0. So in the open circuit, we have a voltage, we do not have current. In short circuit, we have a current, we do not have a voltage. So the voltage here, or the V phase, equal to 0. These represent the phasor diagram which which generated or resulting from the short circuit test. And as you can see here, the value of EA, which is the internal voltage, is equal to IARA plus GXASIA. Okay, so the voltage of the armature here equal to the voltage drop across the synchronous reactance and across the rotor or armature resistance. Okay, usually as we said before, the magnetic flux density or the magnetic flux of the stator here almost cancels the magnetic flux of the rotor. So the rotor or the generated magnetic flux in the rotor, and there is a magnetic flux in the stator will cancel the rotor. So the resulting magnetic flux, after we consider the direction of both magnetic flux in stator and rotor, we got the P net here. The P net value, or the net magnetic flux in the armature winding, we call it the P net here. So as we can see from this graph, so the P net here in the middle, and here we have the B stator in that direction and the B rotor in the other direction. So this will be the B net, and it's actually depends on the value of the magnetic flux which is come from the rotor and the magnetic flux that come from the stator. So an approximate method actually in order to determine the value of reactance, or which is the synchronous reactance of the synchronous generator, there is a method. The first, we need to calculate the value of EA from the open circuit test. As we mentioned before, we said we change the IF and we measure the value of EA. And the second one is and the second step, we need to find the value of the short circuit current. So we have open circuit voltage, we have short circuit current. From these two values, we can find the value of XS, which equal to EA over IA short circuit. Okay, so XS, or the synchronous reactance of the synchronous generator, is equal to the open circuit internal voltage, which is EA, over short circuit armature current, which is IA short circuit. And why only we ignore the value of the RA here? As you can see here, this is IA equal to EA over RA plus GXA, because we said the value of XS is much higher or greater than the value of RA. So as you can see here, XS is much greater than RA, so we ignore RA, so it's easy to calculate the value of XS by using these two values, which is IA and X. So this is the relation or the characteristic to find or the sketch which can be used to calculate the value of XS from the two tests, which is the open circuit test and the short circuit test. The short circuit test show the relation between IF and IA. The open circuit test show the relation between IF and EA or V terminal here. And the XS value can be calculated by dividing the value of EA over the value of IA. Okay, so VA from the open circuit, IA from the short circuit, and XS can be calculated at each point. I can find what is the value of EA and what is the value of IA. So when I divide, I will get the value of XS and so on. Okay, so this is how to calculate the parameters of the synchronous generator, which is RA, XS, and EA. We'll continue in the next video.